Hey everyone, thank you so much for watching Weaviate on YouTube. Today we're going to dive into SQL-PaLM, Improved Large Language Model Adaptation for Text-to-SQL. So before diving into it, maybe let me give you 3 reasons why this paper is worth your time exploring. So firstly, this could really reduce the barrier of entry to using databases. If you just have to write a natural language question like, what is the average age of country music singers? And instead of having to learn how to do the SQL syntax, it makes more people able to access databases. And by people, we also mean large language models and this whole tool use kind of thing. So the second thing I think this is a really interesting paper is just understanding further the zero-shot, few-shot learning abilities of these large language models. They compare their few-shot prompted PaLM large language model with, say, these models that have been fine-tuned on the Spider text-to-SQL dataset, and they're finding that basically they can prompt this model to just instantly outperform the previous models trained with supervised learning. And that brings me to the third thing is I think, especially if you're interested in deep learning research, this Spider data set where they collect 7,000 queries across 166 different database tables for training and then say like 1,000 queries on 22 databases for testing is a really interesting data set for how text-to-SQL is measured. They also have 3 variants of it, Spider synonym replacement, Spider realistic, and Spider domain knowledge. They kind of test this idea of, how do we benchmark how well these models can write SQL queries. I think this is super interesting for Weaviate. Weaviate also has an aggregate API built in as well, so you can do these kind of queries with Weaviate as well. I've tested this kind of few-shot prompt on Weaviate's aggregate syntax, so we'll dive into that and all sorts of fun details. So thank you so much for tuning in, and I hope you enjoy this paper summary. This video will explain a super exciting new paper on text-to-SQL translation, SQL-PaLM, Improved Large Language Model Adaptation for Text-to-SQL. Really quickly before getting into the paper, if you like paper summary videos like this, please leave a like and subscribe to the channel. It really helps encourage us to make more content like this. So let's dive into it with a 2-minute TLDR overview. So the high-level task of text-to-SQL is to translate natural language questions into SQL structured query language questions or syntax. So we take a question like, what are the names and release years for all the songs of the youngest singer? And then we translate that into the SQL query based on our attributes of the table, select song name, song release year from the table singer, and then order the results by age in ascending order and limit the results to 1 for just this youngest singer. So this is the high-level idea, being able to ask databases questions in just a very natural way, and then under the hood, the large language model is translating the natural questions into the structured query language. So one of the key investigations of this paper is comparing the performance of few-shot prompting the PaLM model. PaLM is one of the giant pre-trained large language models, one of the 500 billion parameter pre-trained models. So we're going to be exploring how well you can just few-shot prompt this compared to the performance with, say, fine-tuning PaLM on the Spider dataset, and comparing it with the current state-of-the-art, all the existing models that have been fine-tuned and deployed miscellaneous training tricks and inference tricks to perform this task of text-to-SQL translation. So quickly what that looks like is when you're doing few-shot prompting, in the input, you give it examples of a database schema and a natural language question, and then the corresponding SQL translation. So in this A diagram, you're just seeing 2 examples of this in the input. That's kind of one of the questions of few-shot prompting is, how many examples to give, whether these examples should be tuned to be more in line with the downstream inference. But then what you do is you then have this novel inference, schema 3 plus question 3, and then it generates the new SQL. So in few-shot prompting, it has these references of the task to reference and sort of learn from in the input window, which is one of the super interesting emergent abilities of large language models, compared to the more standard inference setup where you just have the novel input and then you generate the output. So A is exploring the few-shot prompting, B is exploring fine-tuning PaLM on the dataset, the Spider dataset of text-to-SQL translations, and then just seeing single inference, single output kind of setup. So just as a quick additional look at what this would look like, when you're talking about giving it the schema, you're talking about compressing representations like this into text to prompt the model. So say you bolded singer as the table, and then it has the keys, singer ID, name, country, song name, and so on. So interestingly, you say have like foreign keys when you're looking at concert and you need to join, say, concert ID in stadium, singer in concert. So you have a lot of interesting ideas of how you could kind of extend this. And it's also worth mentioning that this is mostly about kind of like a surface level SQL interface, not like the underlying optimization of how the data is stored, but offering this kind of interface in natural language. So this is the idea of taking these questions and then translating them into SQL based on giving it the table as a part of the input. So another really interesting detail of this paper are the data sets that they use to evaluate this. Spider is a collection of about 7,000 training queries, I think 1,000 testing queries across 166 database schemas for training and something like 22 for testing. So they also have these variants of the Spider dataset as the text-to-SQL research community has iterated and learned about these things. So Spider synonym is about manually modifying natural language questions with synonym substitution. So instead of how many singers do we have, and singers might be like too kind of on the nose with the database schema, you say how many vocalists do we have? Ideas like this to try to like test the robustness of how well the models perform when the natural language question starts to deviate from something that's closely aligned with the database schema. So Spider Realistic, that removes the mentioning of column names. So compared to the question, how many concerts are there in year 2014 or 2015, just more natural, how many concerts are there in 2014 or 2015. And then Spider Domain Knowledge is where you're adding domain knowledge. So list all song names by singers above the average age, and then hard to answer age-related question based on the if you only have the birthday column. So you need to like derive birthday from the table and then answer the question by age, and other examples like this. So quickly before diving further into the details of the SQL-PaLM experiments, I want to quickly remind you that you can do these symbolic aggregation queries directly in Weaviate using the Aggregate API. So in Weaviate, if you have a class, like maybe just to continue on this, if you have, say, the singer class, you similarly have these properties where you have, Joe Sham is a text property, or say you have age, which is an int property, or ismail is a Boolean property. In Weaviate's aggregate syntax, you can then access these kind of symbolic aggregations using this syntax. So say you want to see which of your singers appears the most in your data set, you would do name and then top occurrences. Say you want to see the average age, you could similarly do this, age mean to access that, or the Boolean total true, total false, this kind of thing. And then if you want to do this kind of joining as well, you would do, say singer and then say singer, and then the relation is performed in concert, you would do, performed in concert, ... on concert, and then now you're in the concert class and you can keep using all this kind of syntax. So that's how you do this in Weaviate. We're going to look at a few shot examples showing that this exact kind of thing works in Weaviate, which is super interesting. So if you want to do this symbolic joining queries, aggregations of your metadata, you can also do that in Weaviate. There's another super exciting connection of this research with Weaviate. We're going to dive into this more at the very end of the video on some key takeaways, but LangChain Llama Index, they've recently been promoting this self-querying retriever kind of idea, which is really amazing. And what it is you take a query like, what is a golden doodle, and you add filters to make it filtered vector search. To step back a bit, Weaviate vector databases are about building these vector index structures to allow approximate nearest neighbor search at absolutely massive scale. In addition to just kind of traversing the proximity graphs to find the nearest neighbors distance-wise, we also can connect them that match symbolic filters. So say you want to build one index and then have a symbolic property like the source of the index. So say it's text passages, and then you have a filter on whether it comes from Wikipedia, comes from Archive, or comes from Reddit. You can add these filters onto the query, and it will traverse the vector index with that filter. So it's really interesting, the idea of enabling these query routers to either say which of these classes do you want to search through, or what kind of filters do you want to apply on searching through the vector index. So we'll talk about that at the end, but this is another kind of connection to this idea of using these large language models, or just generally the capabilities of language models, to help facilitate the query interfaces. So coming back to the SQL-PaLM paper, let's look at some examples of natural language questions and their corresponding SQL translations, as well as the database tables in reference. So first of all, imagine this question: what is the average, minimum, and maximum age of all singers from France? We have this database table with the tables stadium, singer, concert, singer in concert, and then we need this to produce this query: select average age, min age, max age from singer where country equals France. So the large language model needs to look at the table, look at the keys, infer this country property, and then generate this query. So already, I think something that's really interesting about this, and previewing the Weaviate angle a little bit, is how right now what we're doing with this SQL-PaLM paper is we're just giving it the names of the properties without any kind of description of what the properties are, or say, if it's a categorical property, which of the values it can take on, and maybe some kind of description of the categories as well, or say it's like an integer, the range that it can take on. So a lot of interesting things for extending this further, but right now it seems like just semantic keys is working for this kind of translation, but maybe that's a direction to take this further. So here's another question: show name, country, age for all singers ordered by age from the oldest to the youngest. So again, we take the exact same data schema as the first example, and we translate this query into select name, country, age from singer, order by age in descending order. So again, it needs to do an inference about the age ranking and then produce this order by age descending order. So this is a great example of taking the natural language query, inferring the intent that the user wants, and then translating that into this particularly order by age descending order thing. So next up, we have our first example of needing to join tables together. So we have the question, what are the names of nations where both English and French are official languages? We have this table country, and country has the foreign key code, which is how we join with country language, country code. So what we need to do is we have this, from country as T1 join country language as T2 on T1.code equals T2.country code, where, and then it learns to parse out the English and French are the languages, and then it needs to then get the names from the top of it. It also needs to check this condition is official from the are official languages. So we're already starting to see an example of a query where, doing this query out might require some knowledge of SQL, some experience of doing it, especially to, quickly / instantly translate this natural language query into this kind of thing. So this is a really interesting example of introducing joining tables together in this picture of generating text-to-SQL queries. The next query is, what are the number of concerts that occurred in the stadium with the largest capacity? So now we're doing an aggregation. We're selecting the count from concert where stadium ID equals, and then we have this nested query ID where we select stadium ID from stadium, and then we order by the capacity because we want the largest capacity, and then we want to just limit it 1 because we just want the largest capacity, not like a list of the top 5 largest capacity. So now we're seeing this concept of an inner query, super interesting concept again of translating this into the SQL. Next up, we have a super interesting query, find the first name of students who have both cat and dog pets. And we have the database table student, has pet, and then pets. So what we're going to do is we're going to first subsample from each of the tables. So first we join the student has pet pets tables with the condition pet type equals cat, pet type equals dog, and then we're going to do the intersection of those two tables of students who have cats and students who have dogs to find the first name of the students who have both cats and dogs, or a cat and a dog as a pet. So this is the first case, I think, where we're starting to wade into the waters of query optimization. SQL is built on this idea of relational algebra, where basically you do these like set pruning, set operations that will filter the set. So say you had 1,000 objects in your database table, and this one filter would potentially reduce it down to like 20 objects compared to whereas this other one would reduce it to 500, and then you're joining that with another table. So there's a question about the order of operations for how you apply this kind of set filtering to reduce the cardinality of how many objects are in your databases. Hopefully that was a decent overview. I definitely need to brush up on my relational algebra, but to get the general sense of there's some optimization behind how you apply filtering operations, and then the order in which you apply filtering and join operations. The next query. So this is a pretty complex one. What are the IDs and names of all the countries that either have more than 3 car makers or produce Fiat model? So in this case, we have the union of these two conditions on the database tables. So we're joining together, the countries with the car makers. So we have 6 different database tables in this. So another case of this example particularly is a great example where you would need to have written some SQL to have quickly translated this into this select T1.country ID from country. So this, I think, is the perfect example of why we need these models and how this facilitates this kind of natural language question shown on the top down into this SQL syntax. So quickly before moving on from the SQL query examples, I wanted to run a little test of how well this would work with Weaviate's aggregate syntax. So the way that I structured the prompt is first I give it a description of the API syntax. So the aggregate function is structured as follows. Then give it that same, GraphQL, all possible things you could do with it block, as shown previously, and then I give it the new schema. So I like to play with this Weaviate podcast search example. So I have podcast clip that has properties speaker, content, podcast number, and the duration of the podcast. Then another quick description of the task. Your task is to take a query and translate it to the appropriate aggregate syntax based on the syntax provided above in the data schema. So then a training example, who is the most frequent speaker in the podcast clips, and then this would be how you do that. You top occurrences, value occurs. And so now the test query of how long was the longest podcast clip. So running this live, hopefully it works. So yeah, that's exactly correct. And so we see how it's able to do this translation, and maybe that's not the most confusing query, as we saw some really confusing queries, but just to get a general sense of how this might look with Weaviate and the things we can do with this kind of large language model translating from natural language into structured query languages. So let's get into the data sets that were used to evaluate PaLM's ability to write SQL queries and a little more background on this field of research called Text-to-SQL. So to take a quote from the paper, Text-to-SQL is a long-standing challenge crucial to enhance database accessibility without requiring expertise of SQL. So this angle is the general human accessibility, trying to help more humans use SQL systems as easily as possible, get running as quickly as possible. And then the other angle, Text-to-SQL enables the development of conversational agents with advanced data analytics abilities. So there's a lot of talk about tool use, large language model agents that use tools, and this is about helping the agents make SQL queries, these symbolic aggregations to acquire information, like as we mentioned, like I don't know, I think it was like how many concerts were performed in the largest stadium or things like this, to enable large language model agents to acquire that kind of information from structured database tables. So this research of Text-to-SQL, the flagship data set has been Spider. Spider is the ImageNet of Text-to-SQL, or the beer, the big data set for this research category. Spider contains 7,000 training samples across 166 databases and 1,034 development samples across 20 databases. So having examples of a database schema and then corresponding natural language to query translations based on that database table. So similar to, say, ImageNet C and the robustness corruption tests around ImageNet, Spider has these variants. Spider synonym. This describes manual replacement of synonym substitutions in natural language questions. So sometimes the questions they explicitly kind of match the key in the schema. So they replace this to see how robust these models are when the question isn't so on the nose and talking about exactly the property in the table. Spider Realistic is about removing any mentions of column names in the queries. So similar idea, instead of replacing it with a synonym, you just outright destroy any mention of a column. And then domain knowledge, this one I think is a little more nuanced. This is where you need to kind of derive a property from one of the attributes. So I wasn't completely sure of that. So with that said, let's dive into some examples from the original Spider dataset, which are categorized as easy, medium, hard, and very hard. So characterizing each, train input-output example as easy, medium, hard, extra hard, this is a pretty standard practice in deep learning for programming languages. Like, say, a lot of these data sets constructed on like Code Forces or Leet Code, they also have this kind of categorization to it. It'll be really interesting to do this for ImageNet and all that stuff as well. But let's take a look at the training examples and how difficult they've been labeled as. So an easy SQL question: what is the number of cars with more than 4 cylinders? Just select count from cars data where cylinder is greater than 4. Then a medium question: for each stadium, how many concerts are there? And so I think this graduates from easy to medium, because now you need to join the concert table with the stadium table based on these IDs, and then you need to select the count of the concerts. And you also introduce the group by syntax and grouping the stadium IDs to aggregate the concerts. Anyways, so then a hard question, I think then you're joining together 3 tables: country, continents, and car makers. So extending the joining. You have the condition having as well, which is similar. Well, you have a condition on the aggregation, so maybe that's part of what makes it hard versus easy. And then extra hard, I think you have this nested query not in, where you also have this kind of join in the nested queries, so a little bit more. Maybe there's more to the difficulty levels with respect to queries that have that kind of opportunity to optimize with the relational algebra. I'm not like an expert on this. I'm just familiar with relational algebra, but maybe that's something that could also factor into the categorization of the difficulty of the queries. Okay, so now that we have a sense of what the data set looks like, examples of these questions that are based on these schemas, and then the corresponding natural language to SQL question, the key detail that we're going to be exploring in this paper is how well this PaLM model taken off the shelf and prompted with a task description and a few of these examples, how well can that translate natural language into SQL, and how does that compare with fine-tuning a PaLM model on these input-output pairs? So firstly, let's dive a little deeper into the few-shot prompt. In the appendix of the paper, they have the exact prompts for how they're going to compress tables with the questions and do this few-shot prompting. So we're at the end of the paper, and we're looking at the exact prompt that was used to prompt the PaLM model to translate natural questions into SQL. So the first thing to note is they're going to ablate 2 details: a concise prompt design compared to the verbose prompt design. And this is kind of what I was mentioning earlier, where a verbose prompt design is where you give it the attribute and then you tell it the type of the attribute. I think it could be interesting also to kind of say it's a category attribute to extend this with the different categories. I think this would be sort of essential for that self-querying retriever idea we mentioned at the beginning, but anyways, I think that's getting distracted from this. But so basically, verbose prompt is where you really tell it about, these are primary keys, these are foreign keys, and you give it a lot of information, compared to concise, where the syntax is a little more. Maybe let me zoom in to make it easier to see. Whereas the zoom in is just giving it the values directly. So basically what you're doing is you start off by telling it the task. This is a task converting text into SQL statement. We will first give the database schema and then ask a question in text. You're asked to generate SQL statements. So then here's an example, here's an example. So these are the few shot examples. So they're annotated as, here is an example, convert text to SQL. So then you have the schema values. So in this case, it looks like the tables are separated with this like farm, colon, so this is city. Okay, so that's what that looks like. Then you have the column names associated with the schema. Oh, so you do have the type. So you just have a little more verbose way of saying the type. So sorry if I gave bad information. So then you have the question example. So what are the themes of farm competition sorted by year in ascending order? And then you have the corresponding translation. So you give a couple examples of these. And then when it comes to be test time, you have, here's the test question to be answered, convert text to SQL. You have the new schema, the new explanations of the types of the columns, the primary keys, foreign keys, and then the question, how many singers do we have? And then generate the SQL. In addition to the comparison between concise and verbose prompting, the authors are also going to explore consistency filtering and execution filtering. So to give a quick background before we'll dive into the OpenAI playground and get an example of what this kind of randomness in large language model decoding looks like, consistency filtering is mostly used in question answering. This is where you sample diverse reasoning paths, and then the ones that end up at the same answer, that's going to be the final question. So if it's like mathematical reasoning, and then you're like breaking down the steps of doing the math by decoding different paths in the language model output, then you just aggregate the final answers. It's the most consistent, like say 40 if we're adding numbers or something, and then that would be the answer that you give in the question answering. Execution filtering is unique to programming languages. This is where you sample the diverse outputs, but then you put the outputs through the code executor, and then similarly how many ended up with the same output. So you can use this for SQL, Python, all this kind of stuff. You can take the different code generated and then execute it, and then whatever the most popular output is, that's what will get sent as the answer. Okay, so we're in the OpenAI playground, and we're going to dive deeper into how consistency filtering works. So the idea is that we're going to sample diverse candidates from large language models as we decode them with randomness. We have temperature set to 1, and we're asking the language model, please write a one-sentence summary of Kubernetes for a 5-year-old. Please be as creative as possible. So the first time we ask it this, it says, Kubernetes is like playing with Legos to build a superhero city in the cloud. Okay, so that would be one potential generation. Then we sample another generation. Kubernetes is like a magical box that helps get your work done faster. So that's an example of how we can sample diverse outputs. This is similar to the idea of like tree of thoughts, where you go down all these reasoning paths. So maybe another example would be how many people are in America? Please show each intermediate step as you determine this answer. And then, so this is kind of like something that maybe requires reasoning. So, it's sort of like a hallucination also to ask it to do this. But okay, so it came up with this calculated total number of people. So it's saying, 331,000. So this is like the final answer. So then consistency filtering would be, we just keep sampling from it and then see if it keeps coming to that same 330 million number. I don't know if this is the best example of that, but you see how instead of doing this step 2, it just did it after step 1. You do this kind of thing, but for writing Python code, SQL code, you sample a bunch of different pathways, and then the final answer, in question answering, consistency filtering is just about, is this answer the same? Whereas with code execution filtering, you take the green that it generated, like, write a Python program for bubble sort, and it will write this Python code, and then you would put that into the Python executor, and then consistency of the outputs. So quickly before diving fully into the results, the authors do find a significant benefit by doing this consistency and execution filtering. You see, no consistency down to 77, then the execution filtering 79 compared to up to 83 with the exact matching or the execution accuracy of the SQL queries. So I think this is a super interesting idea this was one of my favorite ideas in, say, the LangChain chains, is taking the output of the language model, putting it into the, say, the Python REPL, and then seeing the output and then chaining where the language model then sees the output and says, oh, okay, is this the output? The authors actually are going to conclude that they didn't find good results of putting the error messages for queries that didn't pass back into the prompt and saying, hey, here's the error that you got for this. But I think generally that's how I personally code as a human, right? Is I see the error and I iterate on the error. So I think there's probably something to continuing to mine these chains of execution filtering. Okay, so let's dive into the results now that we have an understanding of what the Spider dataset is, what it measures, these text-to-SQL translations given a schema as well as part of the input, and we have a sense of few-shot prompting versus, say, fine-tuning the model, as well as, say, this consistency filtering, execution filtering, concise prompt, verbose prompt ablation. So firstly, what we're seeing is the comparison of these few-shot SQL-PaLM versus the fine-tuned SQL-PaLM. So the first interesting detail is that they don't find much benefit by fine-tuning the model. This is actually an absolutely enormous detail because it simplifies using this like crazy. Like if you don't need to fine-tune the models and you don't need to think about like all this stuff around constructing the data sets, the batching, the evaluation or the model versioning, all that kind of stuff that would come with if you really needed to fine-tune these models to get it to do tasks like that. So they do find good performance from the few shot. I mean, it's probably worth noting that, say we're doing the Weaviate we're writing Weaviate aggregate queries, or you're trying to customize this to any arbitrary API. It might not have as much domain knowledge of that in the pre-training data, because surely PaLM in its pre-training corpus has SQL examples, information about SQL in it. So that might be slightly biasing the results as well. But super interestingly, so we're seeing 82.7 from the few-shot model compared to 84.1 from the fine-tuned state-of-the-art. Another kind of reason, though, the fine-tuned state-of-the-art might be a little more interesting is because of this 3 billion parameters. So it's going to be a little cheaper to run. This is another one of the big topics in deep learning is, can we use maybe these models to generate training data to then do knowledge distillation and then have a much smaller model that costs us less for inference? So, is it really worth it if every time we run these queries, it costs us like 2 cents to translate it to the SQL, especially when the large language models are doing them autonomously? So it's an interesting detail, these 3 billion parameter models that are pretty on par, and we could probably use these models in a different way to distill them. But nevertheless, if you're again, as using this example of the Weaviate aggregate query translation, I think that's the most interesting motivating case of the few shot, because you're getting it to learn this new API as fast as possible without collecting training data or anything like that. So here's another example breaking down the performance from easy, medium, hard, extra hard. So probably the biggest takeaway is that you do see this like monotonic performance decrease from easy to medium, hard, extra hard. So that's a pretty interesting detail of this. So especially if you're if you're interested in designing systems like this, if you should probably have some kind of maybe a classifier that says how hard the question is, stuff like this, or just generally logging the queries that fail and overall trying to work to get these models to perform better on the hard questions. But just an interesting thing to see. So then we have the variance of Spider. So again, we have the synonym replacement, the more realistic questions where you deleted any mention of the column name, and then the domain knowledge. I actually wasn't really able to figure out exactly what that is. So comparing with the ChatGPT OpenAI default prompt, this is another really interesting detail. Sorry I forgot to show this in the video, but OpenAI, they have a recommended prompt for writing SQL queries. So what they're showing is they're more verbose prompts with the consistency filtering, execution filtering, improve the performance, and then you see the robustness across the different data sets. Still this 3 billion parameter model is doing a pretty good job, which is exciting because this would be cheaper to run. So then we have the ablation of the concise versus verbose prompting. So interestingly, the concise prompts perform better, which they perform about the same, but like not really giving it these long descriptions of the properties. I think it really depends on this, and I think the verbose prompting is more exciting going forward for the case of filtered vector search with that self-querying retriever thing, because we want to filter it based on properties. So I think it needs to have some sense of what the properties are, like what the potential values that you could filter with. So definitely an interesting topic as well. So here's some discussion topics from the authors. They say that once they fine-tune the model, so converting this to this, the sampling diversity significantly reduced. So that kind of consistency filtering, execution filtering, they had less diversity, and thus that technique on top of the inference was less effective. They also found that, as mentioned earlier, the self-correction, giving it the error messages when it doesn't work, that didn't work that well, which I thought was kind of interesting. And then they find that that there are some problems in the evaluation data set. They give this comment that many of the errors are actually correct according to human experts. So here are some of my personal reflections and takeaways after reading the SQL-PaLM paper. So first of which, I think coming up with some kind of auto API for Weaviate Aggregate, I think this is low-hanging fruit. It definitely seems like something we can achieve with using the OpenAI large language models or the PaLM, not just any of these large language model APIs that we already have in place for, say, the Weaviate Generate modules. We could similarly put this after the query to translate it into these aggregate queries. Which then the next question is how exactly we want to design this pipeline. So maybe it should first take, the auto API should be so open-ended that you just have a query and then the classifier or the language model first says, is this aggregation query or a get query? And then the third thing, so this is kind of just a little layer on like, is this an aggregate query or is this a vector search query? But you can also apply vector search within here to, to say you have tweets and you want to say like, similar to this tweet, you like exactly paste the text for your new tweet, and then you want to aggregate, I don't know, say the likes or something from that. I've given a talk on this at ODSC London. That's also on the Weaviate YouTube if you're interested in that kind of topic of the combination between vector search and then symbolic aggregations. I think it's a pretty interesting topic, but anyway, getting a little distracted. But so then what I want to talk about is, first of all, this query routing idea. So first of all, imagine you have two different classes in Weaviate. You have all the podcast transcriptions, and then you have like the Weaviate code base. And you're asking a question like, how is this particular thing implemented? First asking that question to the language model of which class should you search. Then this idea that I love, which is which filters to add. So this is the self-querying retriever. You ask, what is a golden doodle? And imagine your passages have this attribute about which animal they're talking about. You can then filter the search space dramatically with that. So say we have like, we have like a 5 million scale passages about animals. So then asking it, what is a golden doodle? If you can do that filter where animal equals dog, then you dramatically simplify the search space. So it's a pretty interesting thing about these categories. I think it's most straightforwardly manifested with, like price filters. So say you like take a picture from a shirt from like Louis Vuitton or one of those designer brands, and then you just drop that into Amazon and you say, image search shirt like this for, less than $100, and not having to know how to parse out the where filtering, the large language model under the hood parses that out for you. The next really interesting topic, I think, is connecting search primitives. So, we have these, we have all sorts of different features for search in Weaviate. So say you have like, you obviously have the where filters we just talked about, but you also have vector search, BM25, hybrid search, or say you want to re-rank the search results. Can we kind of automatically construct a search pipeline for doing this kind of thing? And then sixth thing is this concept of generative feedback loops, where we take data from the database, send it to the large language model, and then save the result back to Weaviate. I think in a lot of cases, these, like when you're doing these kind of symbolic aggregations, you might want to save the fact that you derive maybe as a natural language fact into some kind of text corpus. Like I know generally, like when I'm using SQL, like back when I did that kind of thing, if I had a query that was useful, I would save that query for reference later, so I wouldn't always have to remember how to write it. So maybe there's something to that in some kind of connection with generative feedback loops. But overall, my takeaway is I think this kind of idea of automatically writing these kind of aggregate queries, exact same idea as the paper. I think that's also something that we could achieve in Weaviate and is quite exciting. So thank you so much for watching this paper summary of SQL-PaLM. Again, if you like content like this paper summary content, please leave a like and subscribe to the channel. It really helps encourage us to make more videos like this. Please check out Weaviate on Weaviate.io or the open source GitHub repository Weaviate/Weaviate, and please follow us on Twitter at Weaviate.io. Thank you so much for watching.